All right, today we're going to finish section 10.4. We are looking at variation. Last class period we stopped with variation, specifically with variance and standard deviation. And today we're going to pick up on one way in which standard deviations are actually utilized. And that is within normal distribution. So normal distribution is a smooth bell-shaped curve that depicts frequency values distributed symmetrically about the mean. So there are lots and lots of things that are distributed normally. If you were to go to the grocery store and you were to pick up a box of Lucky Charms, and it will tell you on the bottom of the Lucky Charms how many ounces are in the Lucky Charms. You guys know what I'm talking about? All products do this. They tell you how much is inside of it. Well, the amount that's inside of that might not be exactly that amount. Did you know that? It's going to be close, right? But there's some sort of a percentage of error that the company is comfortable with, either a little bit too much or a little bit too little. The same thing happens at your gas pumps. If you go to the gas pumps, they put these little pluses and minuses, how far away from the actual amount you're getting it says that you're getting. And there's a certain tolerable allowance of how far away it can be, and it be okay. And so the more massive a group of data is, the more likely it is to have a normal distribution. So when students talk about, you've heard the phrase before, grading on a curve, right? So grading on a curve did not get its start in what you think grading on a curve means. So if a student asks me to grade on a curve, I know that what you're saying is you want me to round everybody's scores up X number of points, right? It's not really what grading on a curve means. That's not where that phrase at least initially developed. Grading on the curve actually means that you take all the scores and the bulk of the people get C's, and then there's fewer people on each side of that get the B's and the D's, and then fewer yet that get the A's and the F's. That's what grading on the curve actually means. And while it would make no sense in most classes the size of ones that we have here at OBU, it might actually make a lot of sense if you had 400, 500 people in a class like you might have at OU. So you do see sometimes grading on a curve in very large style kind of classrooms. So let me show you what the image looks like for this. It says that it's a smooth bell-shaped curve. So it looks something like this. The peak right here, pretend I got the peak marked well, I didn't, but pretend, is the mean. So you can put mu, or we did X bar before, I'll use X bar. Hang on. And then as we go out in each direction, we actually use the standard deviation to do what's described in the bottom empirical rule. So if we go one standard deviation in each direction, so this is X bar plus S, this would be X bar minus S. And we mark this piece off. According to the empirical rule below, 68% of our data values would lie in this range, like this. 68%. If we go two standard deviations out, so we do plus or minus 2s, so right, X bar plus 2s, and we have X bar minus 2s, and we go this far out. I'll shade it in, I'll use orange. I have 95% of my data in that area that's been shaded. And if I go out 3 standard deviations, I get almost everything else. So X bar plus 3 standard deviations. Over here I have X bar minus 3 standard deviations. And I'll highlight all that in green. So the green comes all the way out. I get 99.8% of my data values. Practically speaking, it's 100%, right? Practically all of them. So if you think about it, and actually when I was a grad student, I taught some classes at the University of Kansas when I was getting my master's degree up there. And I remember being a part of a group of students who were teaching pre-calc at one point. And the grades were not exceptionally good. And we were talking about how do we want to curve them. And we used grading on a curve like this. So nobody's grade went down because of it. They all actually ended up being skewed upward, but not just by adding X number of points, but by trying to make sure that we had, about X number of people, whatever percentage. It wasn't necessarily 68% that we decided, but a certain percentage of our students that got C's. right? We made sure that the middle grouping of students, whatever percentage was we decided at that time, were getting C's. And then we had a percentage out here in sort of this was the B category and this was the D category, right? And so we had that same percentage approximately getting B's and D's, and then we went out from that and did the A's as well. So we actually did that that particular time that I taught that class. So what we're going to do is every time we have a normal distribution question, you're going to draw the normal distribution curve, okay? And then I'm going to show you within a question how we go about using this information. We are always going to use the empirical rule. The empirical rule is only valid if you have a normal distribution, which means something has to say it's normal, okay? So it will say it's normal. That's a red flag. And then we're using the standard deviation and the mean that it gives us, or that we have to create or find if we're working through it in that way. And we have our 68, our 95, and our 99.8%. So as we're taking a look at this first question, very first thing it tells us is assume a normal distribution. Normal distribution where the average phone call in a certain town lasts 8 minutes with a standard deviation of 2 minutes. So as we're drawing our curve, we're going to actually use those values. Now your curve does not have to look perfect, I don't really care, but the values on it should be correct. So my mean right here in the middle should say that it's 8 minutes. And with my standard deviation being 2, it means that I add 2 again, and I do it one more time to go out the 3 standard deviations on the right. I subtract 2 again, and I subtract 2 one more time to get my standard deviations on the left. So far, so good? So the picture itself doesn't have to be perfect, but all those numbers should be right. And then we're going to use the information asked for to get the next piece. It wants to know the percentage of the phone calls that last between 6 and 8 minutes. In other words, it wants this piece. And you will shade it in. It doesn't have to be in colors, obviously, but you're going to shade in that this is the part of the graph that you are looking for. Now, that's not exactly 68, 95, or 99.8, but we should be able to use those values to figure out what that shaded part is. Any thoughts on how we would figure out that shaded part? Right. So it's just half of that 68 region, right? If I went out the other direction, this would be the full 68 right here, yeah? And I have half of it. So you're right, I have 68%. It's divided by 2. You don't necessarily have to write that, but that is what we're doing. And we have 34%. So approximately a third, that's pretty close to a third, 34% of my phone calls last between 6 and 8 minutes. Is that okay? All right, so we have another question pertaining to the same set of information. So you can try to draw it on top of the same graph if you wish. That's okay. It's not bad, especially if you have some colors to differentiate. Or you can simply draw another graph. It doesn't matter to me. I'm going to draw it on the same graph because I do have some colors that I can differentiate between. And I will shift it over here, though. So it's on my right screen. It wants to know the calls that are less than 4 minutes. So in terms of my picture, I'll shade in blue this time. It's these calls right here, right? So ignore the green. That has nothing to do with the question at hand. How can I figure out what that shaded blue area is? And there may be more than one way of doing this. Any thoughts? You're right. My regions do not actually divide evenly, so I can't just divide by 6. So that's a good thing to notice. Could I find this area? What would I do to find that area? The purple part.
We have the 2 standard deviations.
Yeah. So one standard deviation was 68, and we halved it, right? So this image where the purple is right now is half of the 2 standard deviation value, which is the 95%. Does that make sense to everyone? So over here, if I looked at the purple part, I could find this purple part by taking 95% and dividing by 2. So let's start there. What's 95% divided by 2? 47.5 it is. Yes, ma'am. 47.5. So tell me then, one more thing. Let's use yellow. How much area is all of this? Not quite.
50%.
It is 50%. Why is it 50%, Caleb? It is exactly half of my graph. So actually what happens is that I can't use the 99.8 that you were mentioning, Emily, because I want to be able to go all the way down to 0-minute phone calls. And you're thinking about stopping at the 2-minute phone call mark. So we're missing a tiny little bit. But the part that's in yellow is half of the graph, right? So if I have the yellow being half of the graph, whoa, how can I figure out what the blue part is? Right, I can do 50% minus the 47.5. Okay, 50% was everything I previously highlighted in yellow. I know I've deleted at this point. And I want to subtract off the purple part, and that should leave me with the blue part. So what is 50% minus 47.5%? 2.5%. So clearly my graph is not drawn to any sort of scale. It doesn't look like 2.5% at all, right? But that is how we would calculate it. Any questions on those? I have one more of this type. Just on the next page. Okay. Our last one with the same setup, context, wants to know the percentage of the calls that lasted more than 12 minutes. So I've got my same shape here. My more than 12 minutes, I'll do it in orange, would be this piece over here. Yeah, please.
2.5%.
Okay, so why do you think it's 2.5%?
Because it's the same, it's just like reciprocal of the less than 4%, or 4 minutes.
Yeah, so not reciprocal, but the symmetric piece, right? So these two orange pieces on the corners are symmetric, right? They're both 2 standard deviations and further out than that. So whatever I found over here for the blue piece has to have a mirror image to what would happen on the other side where I've now marked my orange piece on the right. So it is also going to be, by exactly the same reasoning, 2.5%. Good job. So there's some beautiful symmetry things that are involved in a normal curve, and you should utilize them when they're useful, and they often are in a particular problem. Okay, now notice on every single one of those questions it said, what percentage? Right? Do you guys see that? Oh, so our answers are in percents. As we shift gears to the next problem without reading it, too far into it, this one does not say what percentage. It says how many students. Okay, that is a different question. We do not get to stop at the percentage on this one. We will have to go a step further. So make sure when you're looking at the questions that are being asked that you're really answering what's being asked. Be careful on that. Okay, so let's read through this one. This one's talking about IQ scores. The mean IQ scores for 1,500 students are normally distributed with a mean of 100 and a standard deviation of 15. How many students have an IQ between 85 and 115? So what's the first thing I'm going to have to do in this problem? Draw a graph and label everything, right? I need to know where all those numbers go. So I've got my graph. What goes in the middle? 100. What's my standard deviation? 15. So we need to go out. Well, I won't even mark it like that. I'll just mark it on the bottom for now. 15 in each direction. So this is 115, 130, and 145 on the right. On the left, it's 85, 70, and 55. Is that okay so far? Okay. Now, our question wants us to go between 85 and 115. So here's 85, and here's 115. So percentage first. What percentage of our values lie in that shaded red region? Yeah, so that's even easier question than the last ones we were doing, right? It's 68%. Now, we don't get to stop on this problem at 68% because we're supposed to be finding the number of students. So there's two ways that you could find, at least two ways, I'll remind you, that we have found percentages into the number of quantities later. So one option is that you can remember that all percents are a value out of 100, and our number of students is a value out of 1,500. Okay, so you can set it up like a proportion. This is one way to do the problem. Grab your calculator, of course, if you'd like. And you would cross multiply. We would get 100x equals 68 times 1,500 is 102,000. And you would divide by your 100 to give you 1,020 students. So we did this with proportions. We did that back in chapter 7. Another option in how we did things back in chapter 7 is that we took percentages, right, like our 68%, and we turned it into a decimal, namely 0.68. And we used that decimal to multiply by our number of students. The calculation process is actually quite similar. The written down process might be a little bit shorter. We still get 1020 students. Okay, so any questions on that? So there's this one extra step at the end after I find my percentage where I have to multiply to figure out how many students I get. Possibly do some division if I've used proportions. Okay, so should have done it before I made it all red. Maybe I can erase the red. Let's see. Yeah, that's not going to do it. That's not bad. Okay, so here's my graph originally. This one wants to know how many students have over a 145. So I don't hardly have 145 even on the scale. It's way over here at the very right-hand edge. It's this red piece now. That little corner. Okay, so this is kind of like what I did over here to find the blue piece, right? I've got an edge, a corner, or to find the orange pieces here. But it's not beside the 2 standard deviations, it's by the 3 standard deviation mark, right? So what would I go through to figure out the percentage first for that red shaded piece?
Would it be the 99.8, or subtracting out from 100 and then dividing it by 2?
You definitely can do it that way. So 100% is the entire graph, right? 99.8 will give me the part that's sandwiched in between the 55 and the 145. This is 99.8. What that will actually leave is it will leave both little corner pieces, and I'm only supposed to have one of them. So we can take the 100% minus my 99.8 and then divide that quantity by 2 to get just one of those two sides. So go ahead and do that. Take that 100 minus 99.8 divided by 2, and what do you get? Huh?
1%?
You're close. 0.1%. Right? That subtraction on top actually ends up being 0.2, and then I get 0.1. So you can either set it up as a proportion, 0.1 over 100 equals x over 1,500. Or you can set it up as taking that 0.1 and turning it into a decimal. I know it's already a decimal, but it is a decimal inside of a percentage. So I have to move the decimal 2 to the left. So it ends up looking like 001 as a decimal in its decimal form. So you can take the decimal point with the 001 and multiply it by 1,500. Either of those are acceptable ways to find the solution for the number of students. What do you get? 1.5. Okay, so I'm supposed to be finding a number of students, and I just found out there's 1.5. So it's kind of a weird number. We're not going to tell somebody that there's 1.5 students in my school that have a high IQ over 145, right? We're just going to use normal rounding rules. 1.5 would round to 2. So we're going to say that there are 2 students. Okay, does that make sense to everybody? Just going to use normal rounding rules. We're not going to try and figure out, well, should it be 1? Because it's really not 2. Maybe it should be 1. We're just going to use the rounding rules and go with it, okay? All right, we have one more with this context. We want the students with an IQ between 70 and 145. So 70 is here, and 145 is here. And what is it about this particular one that makes it a little bit different than the ones we've done? Right, so how many standard deviations do you have on the left-hand side, Emily?
2.
Okay, this is 2 standard deviations over here. And how far did we go over on the right? 3. So it's not balanced, right? I don't have an equal disbursement on the left and then on the right. And not that I have on every problem, but any problem where I went in both directions I did. It was balanced, and this one's not balanced. So instead of taking a look at it the way it is, it would be far easier for us to look at it kind of like we did over here with that green piece. Let's just find what happens to get from the middle over to each one of them individually and then add them together. So I can take from the middle to the left, the 2 standard deviations is my part in orange. And how would I find the orange percentage? 95% divided by 2. We'll come back to that in a second. How can I find the blue percentage? Right, 99.8% divided by 2. And once I find these, what am I going to do? I'm going to add them together. We already did 95 divided by 2. We found that earlier. That's 47.5. What is 99.8 divided by 2? Got 49.9. Does that sound right? Yes? Cool. And then we're going to add those together. So I get 97.4%. Am I done? No, I'm asked for the number of students. So I will either do a proportion and take the 97.4 over 100 times x over 1,500, or we will take 0.975 as my percentage in decimal form times my 1,500 students. Either way, we'll get the same quantity. How many students will this yield? 1,461 students. Okay, any questions on that? Okay, so normal distributions, big thing. The last thing in this section is percentiles, and percentiles is another really important thing, educationally speaking. So it's very interesting because standardized tests are typically done in percentiles. That's one of the places where you see them used. So if you have a student who takes some sort of standardized test in your classroom, and there are bukus of standardized tests at every level you're at where they take, whether they're measuring their reading comprehension, whether they're measuring their math facts, right, their ability to add or subtract, or some other quantity, percentiles come into play. So a percentile actually shows a person's score relative to other scores. For example, a score in the 90th percentile means that approximately 90% of all other scores are lower than this score. It doesn't mean you got 90% of the problems right. You may have gotten it. You may have gotten 72% right. You may have gotten all 100% right. and still be in the 90th percentile. Okay? Percentiles are very unusual. And so it's all about comparison to everybody else who took it, which means there have to be people in the lower percentiles to even make that mathematically possible, right? You can't be tall if there's nobody short. Right? You can't be in the 99th percentile if there's not somebody over there in the 1th percentile, the 1st percentile, right? That's how percentiles work. So what we tend to see when we go in for like parent-teacher conferences, which you guys will be on the other end of that, where I was on a parent-teacher conference on the parent side recently, is the teachers like, I'm really just hoping they're somewhere close to the 50th percentile, because that means they're on target with, and it's an average. I'm looking for them to be kind of on target with the rest of their grade level, right? Something lower than that might be cause for concern. Something higher than that might be cause for celebration, and it might not matter at all because it's a standardized test, and they don't always measure what they think they're measuring. So percentiles is a big deal in education world. Percentiles is also a big deal in growth charts. It's another place that I personally have seen them used significantly. So when you guys have children, you take them in. The pediatrician likes to put their height, their weight, and when they're really little, their head circumference on a growth chart. Okay? What they're trying to make sure is that all of a sudden it didn't go from like the 20th percentile to the 70th percentile, because if so, you might need to cut back on their food, right? Or the other way, it might not want to go from something a really high percentile to something that's a really low percentile, because there might be a problem, right? That might be a red flag for a pediatrician to say, there's maybe some malnutrition issues going on. Do we need to find some support for you in the community for food for your kid? Right? That's a problem if there's a red flag in that area. They also like to compare between the height and the weight. So I have a child in my home, my 8-year-old, and she's in like the 2nd percentile in weight. She's the skinniest little thing you ever saw. I mean, I think that's about how big her legs are around. Like her ankles may not even be that big. It's crazy. But her height, she's very tall. So she's in like the 75th percentile in height and like the 2nd percentile in weight. What does that mean? It means she's skinny. That's what it means. I mean, really. But they don't match up. My son, the one who's 13, when we adopted him from Ethiopia, his head circumference was abnormally large. To this day, he has a little bit of a complex about it. It does not look large if you just look at my son, but it did when he was little. It was significantly high. And so it warranted testing. It warranted MRIs and CAT scans, both in Ethiopia and then when we got him home. It warranted careful tracking to make sure that it wasn't increasing in size, that it was somehow leveling off or getting close to its own, natural growth chart curve at that point. And so they use those kinds of percentile growth charts, and it's all based on percentiles, in order to track and make sure that a child is growing properly. And we do it in education to make sure that their education is growing properly by the same time, right? So my daughter tested at the 17th percentile in reading. And it's weird because, she reads to me and I don't notice any problems. And her teacher's not concerned. But she probably will be concerned if she takes the test, 3 months later or whatever, and it's still at the 17th percentile. We got to talk about it then, right? But if it's gone from 17th up to 30th and it's showing growth, that's what we want to see. You want to see growth on the percentile chart when you're looking at education. So when we're looking at this example, we have Junior. Junior is ranked 50th in his graduating class of 325 students. Liz was in the 75th percentile of the same graduating class. Now, these are both ways of sort of visually or mentally thinking about their comparison to the rest of their class, right? Where are they in sort of the line from number 1 down to 325, or where are they in terms of percentiles? So the question that it's being asked is which student had the higher GPA. So we have to compare this data in the same way in order to make the statement that we know to be true, right? We have to be able to either say, I know this because this is both of their percentiles, or I know this because this is both of their class ranks. It doesn't really matter which direction we go, we get to pick. So do you guys want to calculate percentiles, or do you want to calculate class ranks? We're going to do it one way, and then we're going to do it the other way. So pick one for me to start. Rank. Okay, so if we're doing rank, we know that Junior is ranked 50th. So that's the one we've already got. So here's Junior, and he's 50th. So what does it mean for Liz to be ranked 75th percentile? So Liz at the 75th percentile means 70% of the 325 students are below Liz. How can I find out how many students that is? How do I find what 75% of 325 is? Okay, so either proportions or we'll use the one that Caleb mentioned, which is my 75% as a decimal, 0.75, times my 325 students. So if I take 0.75 times my 325 students, I get 240, we're rounding, normal rounding rules, 243.75, so 244. So there are 244 students below Liz. So how can we figure out where Liz is? Right. There's 325 students total, including Liz, minus the 244 that are below Liz. And I would have 81. So Liz is 81st, right? Junior is 50th. Who has the higher GPA? Yeah. Junior has the higher GPA. Okay, so we did that by turning it into class rank question, right? We can also do it in terms of percentile questions. So I can look at the percentile that they're at. So Liz is 75th percentile. Don't write 75% as 75th percentile. Junior is ranked 50, out of 325. Okay, his percentile is the percentage of the student body that is lower than his GPA. How can I figure out what percentage of the student body have a lower GPA than his? In a second, we need to do something else first. How about a different question? Can I figure out how many students have a lower GPA than junior? Okay, so 325 minus my 50, right? He's 50, the top 50 students, which would be 275 have a lower GPA. Does that make sense? Because percentiles is always calculating how many people are below you. 50, really namely 49, would be calculating how many people are above junior. I don't care how many people are above junior if I'm finding percentile. I care how many people are below him. So 275. And then we can do what Emily suggested with percentile, or with proportions. There's 275 people out of the 325 lower than junior, right? And we want to know what percentile that is. I'll call it P over 100. Again, not the only way to do the problem, but proportions do work nicely the way that this one particularly is set up. So we can cross and multiply. So I have 325p equals 27,500. I'll divide by my 325. And what did you guys get? Okay, so 84.6 something. Percentiles still have to be measured in like a whole number value. That's how percentiles are always done. They don't do decimal point kind of things. So we'll use our normal rounding rules. So we would say 85th percentile. So he's in the 85th percentile, while she's in the 75th percentile. So in the 85th percentile would be a higher value. So again, from this perspective, thinking about it this way, junior is higher, higher GPA. Because he has the higher percentile. Any questions on that? Yep, Kaylee.
So with GPA, there's not like 100 possible GPAs. So would there be some percentiles that didn't have people in it? Or like in my high school, there was like 11 of us that were
Ranked number one. Yeah, so it's a very interesting thing because you cannot be in the 100th percentile of something. That's not even a thing. So it can always be like 99% or below you or something like that. But in your case, that's how my high school was as well. We had 9 who were all ranked at the same height. And then it was out of 230 something or whatever students we had graduate. And so it'd be very interesting. So even though you can be ranked first, it might not be the 100th percentile. In fact, it can't be. The best you could get would be the 99th percentile without rounding anyway. And so it still might even not be that high as a 99th percentile if you have a bunch of people at the top level at that. Yeah. Percentiles are very interesting.